Hi, I'm Carly McAvoy. For this activity, you should have watched the two videos that are listed here in this document explaining what a Hamiltonian path is and a Hamilton circuit is. A path, we want to traverse every vertex once and only once. We don't care about the edges, only the vertices. When we're talking about vertices and edges, we're talking about in a picture like this, the vertices are these points of intersection between two or more edges, and the edges are the straight lines. So it would be nice to watch those. I think she does a really nice job of explaining that and showing you about those two things. In a circuit, the difference is wherever you start, you have to finish at the same point. A complete graph is a graph where every vertex is connected to every other vertex. Every complete graph has a Hamilton circuit. Sometimes people talk about Euler circuits, but there are many applications for Hamilton paths and circuits as well. When you want to optimize your city bus route or warehouse deliveries, you're concerned with the edges of your route, and that would be about Euler circuits. But when you're concerned with your salesperson visiting 6 different cities in the most efficient ways, you're concerned with the vertices. You want them to make it to the cities. You don't care about that they've driven around every road between those cities. So that's about the vertices. Hamilton graphs are extremely useful in computer graphics, and one application involves stratification of triangle meshes in computer graphics. Now this may be something that goes right over your head. It does mine. This is a quote from David Epstein. But they can be a useful way to organize data and reduce communication costs. Google uses Hamilton circuits to organize hyperlinks for its search engines. And graph theory is used to find communities in computer networks. There are puzzle games, and there's some listed here that use Hamilton circuits. In Grand Tour, you must find a Hamiltonian circuit in a grid of points in which some of the edges are given as shown below. Maybe you've played some of those games that have used that. One of the things we talk about when we're talking about Hamilton circuits and paths is a weighted map. If you were wanting to visit a city and wanted to see 4 different sites in an efficient way, such as A, B, C, and D, it wouldn't be very efficient to drive all the way up, back, down, whatever. You want to find something that gives you the most efficient. You want to drive as little as possible, so you would devise a route that starts at one point, visits the others, and returns to your original point. That method is called brute force, where you find all possible routes and then you calculate the value by adding the mileage for each. For instance, if I went from A to D, the mileage is 6, so I would put the 6 there. Then from D to B, I would go here, and that's 3. And then so on up to C and back to A. So the total, when I add those up, is 20. But if I did a route from C to D to A to B to C, notice I'm starting and ending at the same place, that would be 18. And so you just find all the different routes and then decide which way you're going to do, which one will be the better one. That's brute force method. Another algorithm that I like is the greedy algorithm. In this method, you always choose the next vertex that is closest to you so that you minimize your distance with each choice. So for instance, let's say we're starting at E. Here's E right up here. Starting with the greedy algorithm, and these are not to scale, and they usually are not. So you want to look for the edge that has the smallest number next to it. And so from E, the smallest number is 1 down here to B. So we would go from E to B because 1 is our least choice. This one's 4, 3, 6. So we would do this. And now we've got to B. We say, okay, now we want to go to a new place. But we can't go back to E yet. We don't want to do that. So we're going to go to the next. We have 7. We're not going to use the 1. 8, and then 2. That's the smallest, so I go to C. And then from C, I'm looking for the smallest, not retracing my steps. And the smallest that I see is the 5 over to A. And then at A, I'm looking to not retrace back to anything I have done yet. And so from that, I want to go back to D. I don't want to go back to B or C because I've already been there. Does that make sense? And then from D, I'm going to go back to E, 20. In each case, I chose the edge with the lowest value. I had to go to a vertex that had not yet been visited when I returned to my starting point. So that's how you're going to do those. Have a great day, and we'll talk to you next time about graph coloring.